Let's first suppose that we have a string stretched out with a tension T. Tension T at this end in the horizontal direction, tension T at this end in the horizontal direction. Now if we pull up on this end of the string, just start pulling up and keep pulling up, then the disturbance will travel along the string at velocity v, and after clock time t, or after time interval t, the disturbance will be at a distance vt along the string, and will be at a distance vyt in the vertical direction here. Every point between here and here will be moving in the vertical direction with the same velocity vy. The result is that we're going to have increased the momentum of the string, okay, by vy times whatever the mass of this length of string is. Now we assume that we're exerting a force Fy in this direction. If we exert a force Fy in this direction, then the tension in this part of the string will actually be a little greater than T. And the proportionality of these sides here will be the same as the proportionality of Fy to T here. That is, we have a little vector here, a tension vector, that has vertical and horizontal component, and that vertical and horizontal component are in the same ratio as the Vyt to the Vt. This is because the string has to be in the same direction as its tension, and that's what we'll have there. Now let's calculate the momentum here. What we're going to do, what we're leading up to, is the impulse momentum theorem. We know the force, we know how long the force has been exerted, so we can find the impulse of this force, which is just Fy times T. If we can express the momentum of this segment of the string in the direction of Fy in terms of this velocity, which we're going to do in a minute, in terms of the velocity v, then we can determine v from the impulse momentum theorem. Okay, how do we do that? Well, the momentum of this length of string is equal to what? Well, first of all, it's the velocity times the mass of the string. How do we get the mass of this segment of string? Well, we know the length, it's Vt. If the length of the string is Vt, then if we know the mass per unit length, mu, we can multiply the length Vt by the mass per unit length mu and get the mass of this hunk of string here that's moving with velocity Vy in this direction. So its momentum will be Vy times Vt mu. Now, what's the impulse? Well, as we said before, the impulse that created this change of momentum is just Fy times T. Well, this impulse then has to be equal to this momentum, and we're going to easily be able to solve for V as soon as we do just a little bit more work with this, okay? Now, as we said before, the proportionality of Fy to T is the same as the proportionality of Vy to V, which of course is the same, well, it is the same as the proportionality of Vy to V because of what we said before. Okay, this is in the same proportion to this as this is to this. And of course that means that Fy over T is Vy over V, so Fy is Vy over V times T. Just the proportionality of the y velocity to the velocity of the pulse. Okay, whatever that proportionality is, we multiply that by the tension, and we see the force that we need to exert in this direction. So we got an expression for Fy that we can put in here. We see that the impulse will therefore be Vy over V times T, times little t, times big tension T times little t, and that'll equal our momentum. And when we put those two together, we see that Vy over V times T multiplied by tension T multiplied by the clock time T is equal to Vy times Vt times mu. If we multiply both sides by V, we'll get a V squared over here. Put everything over on the other side, we end up with the Vy dividing out, and we simply end up with the square root of tension over mu. And that's why the velocity of a pulse in a string is the square root of T over mu.